Good morning. My name is Jon Tupitza. I am a senior cloud solution architect here at Microsoft, and I specialize in Azure machine learning and data science and artificial intelligence. But to kind of dovetail on Frank's kind of story, I came out of a background of software engineering, some infrastructure to go with it, and then a lot of data systems, SQL Server, a lot of business intelligence, and a lot of data engineering as we customarily gathered data from various sources and used them to populate data warehouses. And now, without going too deep into those infrastructure design patterns, now we're still sourcing data from all over the place, even more places than before. Using them to do descriptive and diagnostic analytics, which is business intelligence, but also using that data to do predictive analytics. And so that's what we're going to talk about a little bit here this morning. And now I'll duck off the screen and we'll focus on what we have up here on the slide deck. Now it wants to. There we go. So before we get too far, we should probably talk a little bit about what's involved in data science in the first place. What is it that we're going to automate as we accelerate our data science projects? Well, without a business understanding, we can't get very far. If we don't have a problem, we're not going to find a solution to a problem. But, we really start to get into the heavy lifting when we try to acquire data, locate it, load it, prepare it, explore it, try to identify what data we have could potentially be used to make a prediction, high efficacy, a very accurate prediction. And we have to go through this business of trying to figure out which machine learning algorithm is going to perform the best, which combination of our features, that is, the columns, if you will, in our data is going to correspond to our what we want to predict, our outcome. We might have to engineer some of those features. We'll talk a little bit about that in the rest of the presentation. This is very, very iterative and exploratory, and it takes a lot of time. Frank was saying it can take a very long period of time to do this manually. And what we would love is something that's a little quicker. A little quicker to business value, especially here at Microsoft. We don't sell our work to people. We try to help partner with them as business partners and help them be more effective and achieve higher levels of their business value. And so you can see here, getting to the deployment involves quite a bit of work. So in Azure, it doesn't really look a lot simpler. We've got to go get data from SQL and Cosmos and files and IoT services and all kinds of sources and use them to build and train models, either by hand or using AutoML. We've got to be able to set up infrastructure in order to facilitate that training. Sometimes it's a large amount of data. Sometimes it's complex data like photography and things like that, video. It just requires far more compute than we would have on our desktop computers, no matter how robust we can make them. We got to be able to validate whether or not, deploy and validate that machine learning model and make sure that it's performing to a high level of efficacy, so that we're not misinforming people with our predictions. As a data scientist, one of the things we like to say is that data science and machine learning allows us to make bad decisions with greater certainty than ever before. So unless we go through a validation process to make sure that those models are performing well, we're actually degrading business value, not increasing it. And then eventually we've got to push it out into a production environment, which could be on a Kubernetes cluster. It could be on an IoT device like a drone or a camera, or out onto an IoT sensor on a pipeline or on a factory floor. And even more importantly, then we have to monitor that model and ensure that it continues to perform as designed, because data can change over time. Even as we're responding in the business environment to the predictions we've made, it could begin to skew the other data, the data that we use to make the predictions. And so we have to monitor our models and retrain them on new data occasionally and determine whether or not we need to update them. So there's a lot of work there, even without automating the build and train the model step. So that brings us to the fact that the number one challenge really right now is that there just aren't enough data scientists to do the work. The demand continues to increase as the idea of, using predictive analytics is more and more attractive to our customers. But, I see that there's an interest from people becoming data scientists. But as Frank was mentioning, really, there's a pragmatism. You can have a tweed jacket and know a lot about statistics, but that doesn't render business value. As somebody myself who's done data engineering for 15 or more years to supply decision support for important life or death things like, the military as they've been out there in the world, and some of our other federal government customers, and the crucial decisions they make to support national security. You need to have that pragmatic background and being able to do development work with programming language, understand the limitations and capabilities of hardware configurations and cloud configurations. There's a whole lot out there that's really necessary, and there's just not a lot of people that have that background. Even the people who are, have PhDs in data science and machine learning, they're just, you can count them on your fingers and toes, and then getting people, as Frank mentioned, practitioners, people who actually, people who can roll up their sleeves and actually get it done for the customers. Yeah, I don't feel insulted if somebody calls me a data science practitioner, because, I'm not talking about it, I'm doing it. But anyway, you can see some of the requirements that people need to increase their productivity. Automate that process of selecting features and tuning hyperparameters. Now, for those of you unfamiliar with the term, a hyperparameter is a configuration setting that is part of a specific machine learning algorithm. It controls how the machine learning model learns, how it does its learning. There are configuration settings, and they can have very complex combinations of these hyperparameters, and so there's a lot of iterative experimentation just getting that right. Trying a bunch of different models, algorithms, like whether they're linear or tree-based algorithms, and there's various flavors of them, if you will, and you could end up doing hundreds of permutations to find the best convergence of the features and the hyperparameters and the algorithm to get the model that you want. And there's processes involved in validation that need to be automated to make better use of time, and then there are automation around tracking the experiments, because you can easily reproduce your work when your own efforts. And in the early days, we would very often use an Excel spreadsheet or write things down on a piece of paper, writing down a bunch of metrics to see which one of our models perform better than the other. And then just sort of a mechanism, as we spoke to, continuous integration and deployment to get that out into the production environment and to maintain it, to maintain and look for data and model drift, and then determine when to kick off a pipeline to redeploy that, retrain and redeploy that. There's so much work to do that, this is the big challenge in the marketplace. But, that being said, most people think of automated machine learning as just, hey, it automatically barfs out a model for me, so that means I don't need a data scientist. Well, as Frank said, it could take longer, but if getting the right decision is critical, potentially, say, in the healthcare industry, where it could be a life or death, you really need to have somebody who knows what they're doing, who can validate what's being produced, even if they are using AutoML. So although AutoML enables data analysts and citizen data scientists to generate their own models, for professional data scientists, machine learning developers, it also helps us to quickly evaluate whether or not the data that we've been given is going to be sufficient to produce, I'll use the word accuracy generically. Fellow data scientists understand that's a metric, and uh, and it's not the only metric, and not often the best metric even, but I'll say the accuracy of the model, and whether or not to go back and find more data or better data to train a more effective model. It also allows us as data scientists to quickly identify which modeling algorithms have the greatest potential to produce those highest performing models, and therein provides a starting point for further model tuning. And so we're going to look at some of that as we move along. So as we get started with automated machine learning, you can see there's a process where first, in the Microsoft environment, at least, we have to create an Azure machine learning workspace, and we have to provision a compute cluster and a compute instance. So a compute instance is like a virtual machine in the cloud that we use as our workstation to do our development on. And then even though we're using a browser on our laptop or our workstation, the VM with the software on it actually resides in the cloud. And then we need to also produce a compute cluster, which could be one node or 32 nodes, depending on what we're trying to train and how quickly we expect it to return. Then we have to go find that data, much like the life cycle we spoke of earlier. Go create a data set and explore that and use it to train a machine learning model. And then eventually we want to deploy that as a service and test it and begin to run inferences against it. So as we move forward, let's take a look. I'm going to, as soon as I can find my. So hopefully everybody is now seeing my my browser, and you can see I've produced a number of resource groups, and in this one I've created a machine learning workspace, and I'm not going to show you how to create one because it's like creating anything else in Azure. It can be done manually here in the Azure portal, or it could be done with an ARM template, or it can be done using the command line interface, and it can also be done from a Python notebook running locally on your machine, your local workstation. You could use that to provision a workspace. But when you provision a workspace in Azure Machine Learning, you're going to automatically get a storage account. You're automatically going to get a key vault and application insights, which helps with the model training and with the monitoring and the drift detection. And then you're going to have an Azure container registry to register your machine learning models with once you've developed them. And so this automatically gets generated. And so in your environment, if you have a corporate environment, you may be using a centralized key vault, and you can point to your own corporate key vault if that's the case. You may already have a container registry, and you can point to that. And you may even have other storage accounts, but the machine learning workspace will always have a default blob store for its own metadata. Think of it being a bit like the master database in SQL Server. It needs this storage account to keep track of itself and its own metadata. You can register other storage to your machine learning workspace if you need to go get some data. So I would double click this, but it's just going to get me to an Azure Machine Learning portal interface. And so you can see where we have a lot of different tasks available, and a bunch of them that I've run also. But what we're going to do is just show you that we have compute resources. I'm not going to create new ones, but I have a compute mechanism here, which allows me to open up a development environment in Jupyter Lab or Jupyter Notebooks, or even in Visual Studio Code. And if you're a dyed-in-the-wool R developer, you can even open it in RStudio. I very frequently just open it up in Jupyter Notebooks. It's a very comfortable environment for me. But we also have produced a cluster out here that we're going to use as a training and development target. So, again, you kind of do your development work on the compute instance. It's kind of like your virtual workstation, and then you do your heavy duty lifting, if you will, on your compute clusters. So I'm not going to really create these for you, but you can see it's pretty typical. You just open it up and specify a location, what region you want to be in, and whether it's GPU or graphic processing units are very useful if you're doing computer vision and deep neural network development. So, but we're not doing that. Today we're going to use some simple tabular data so we can use a CPU. And you can choose whether you want to select from recommendations or look at everything out there and just pick one and say next, and boom, you got one. So I'll spare you that because it's straightforward and easy enough, and you can also do it from a Jupyter notebook while you're doing your development work. Okay, so the next thing what we would want to do is create a data set. And so in here, you can go to the data sets, and I've already created one, but we'll show you how to do this. You can do your development work entirely from like a CSV file or a JSON file or a Parquet file that's resident on your system. But if you're going to do iterative development, you may get to it over and over and over and have to redo a lot of your initial work. So even in code, we very often will register data sets. So we can create a data set, and in this case, I'll choose from a local file, and I'll call this daily bike rental, just to give it a name. And although you have the choice of having a file, the only way you can actually use, especially automated machine learning, is with this tabular data set. And it's essentially applying a schema, if you will, to data that's coming out of a file-based source. And as Frank mentioned, you create a schema when you need one. And then you can go ahead and make some choices like, again, I'm going to just let it go on my default workspace blob store, but I can create and register new data stores if I need to. And I can just go and look up a file here. It's really super straightforward. I don't see how any of you probably would struggle through this. But, this is just how you go about getting some data into your, into your environment, your machine learning environment. You click next, and it'll go out there and parse it and take you to makes a lot of good judgments. It sees that it's comma delimited, it's UTF. I can say that all of my files have the same header, or you can combine them or say there's no header. In this case, I'll just say that only the first file has a header. I'm not going to skip any rows, and none of them wrap. If you had a line of 10,000 columns, if you will, then it might wrap to multiple lines underneath the headers, and it would become highly confused if you didn't tell it that it had multiple lines. But in this case, we don't have that. But we can get a good idea of what our data looks like. We have an index, and we have a time date that's been broken out. This is a fundamental feature engineering technique. Raw dates aren't very good for making predictions, but a day of the week or the month of the year, the seasonality, or whether it's a weekday or a weekend, these very often can have a high level of impact. Holidays, again, you can see, just as I'm saying, it's pointing out weekdays and working days, or the weather, the temperature, some things like that. And at the end of the day, the number of rentals. And this is what we want to predict. This is what we call a target frequently, or a response. And this is what we want to predict. And what we're doing is we're trying to make correlations between all those inputs and this output. And so in this case, because we are predicting a continuous number, we know now that this is going to be a regression job rather than a classification job. It could potentially have been a time series job, but a time series job would actually need a time date stamp column to make it time series. And for those of you who are unaware of time series, it's basically like predicting into the future at any given time and being able to view the trends. Think of a line chart where the line spikes up and down over time, and you can use that to make some get some understanding of not just what something will be in the future, but the trends between here and there, and gain some idea from that. But nonetheless, we're just bringing in some data right now, but we've already seen the data and learned a lot from it. What are our inputs? What are we trying to predict? And what type of job it's going to be, regression, classification, or time series. So we'll go ahead and click next. And here we have an opportunity to make some changes in terms of the data type. Sometimes we'll get data types that are numeric, but they're really categorical data, like small, medium, or some representation of something like small, medium, and large. In this case, I know that all of these are good, so I'm just going to click next, but you could make some changes here if that made sense. That gives you a, typical, screen that shows you what you're going to get, the decisions you make, and you can choose whether or not to profile the data after creation. Know that profiling data does consume some resources on a cluster and can take a little bit of time, not a ton of time, but a little. So I'm just going to overlook it this time and just go ahead and create that data set. Okay, so that's how we went about the business of creating and registering a tabular data set in Azure Machine Learning Services. And we also looked a little bit about compute resources. Now I'm going to go over this a little bit because, we can choose using Azure Machine Learning to train on our local computer, on a remote resource, as I showed you, the compute instance, and we can do the larger heavy lifting jobs on not only an AML compute cluster, but we can also do it on an HD Insight Spark cluster, or we can choose Databricks. We can actually register an existing Databricks cluster with Azure Machine Learning Services and do the heavy lifting over there using interactive Spark. We could also, it's a little long in the tooth, if you will, but Microsoft has virtual machines called data science virtual machines that you can also register that as a compute target and a development target. So there's a lot of different support and choices there for people to make if they feel inclined to do so. So, we talked a little bit about that data preparation, a little bit of feature engineering, and this is kind of going to be out there for your reference, but raw data very often doesn't quite cut it. So we saw how we could take a date time and parse that out. That's right in our raw data set. You can find yourself with missing values, and you can choose whether you want to simply drop a row because there are too many, not a numbers or nulls in that row if you have enough data. You could choose to not include a feature or a column because it's too sparse. There's too many nulls in it. Or you can use mathematical algorithms, basic ones like mean or median or mode, or other ones that are more algorithmic that take into account the statistical distribution of data in that column through the populated columns and use it to impute new data. But, if you have enough data, enough observations, enough rows, very often the smart thing to do is just drop the rows, and train on the data that you do have that is good data. If you don't have a lot of data, then you might want to resort to some imputation. Scaling and encoding have to do with scaling is what I take a data that I may have numeric columns where their range is all over the place, that some could be all negative and some could be all positive. And what we want to do is either push it into -1 to +1, or between 0 and 1, or to distribute it normally. In other words, it would have a mean of 0 and a standard deviation of 1. We might want to take small, medium, and large and turn it into 0, 1, and 2, if you will. That's an example of label encoding. We might want to generalize data where we take a birth date and turn it into their age. And even that may be too many. We might want to put those into buckets or bins using discretization and create age groups. So there's a lot of different feature engine techniques out there to prepare data, and AutoML can do some of that. There is featureization as a choice when we go to build a machine learning model. There are under the covers algorithms that are being used to choose which of those features have the highest level of correlation to the target, to that outcome we're trying to predict. And I'm not going to linger on these because we'll run out of time, but they're here for your reference. You can see here, there's a univariate method where we have not built a model yet, and we simply change all of the values in a column to each unique value iteratively and measure which of those values have the strongest correlation to the target. There's another one called permutation importance, where we actually do build a model. Generally, it's a tree-based model like a random forest or a decision tree, and we randomly shuffle around all of the values in each column in order to break its dependency, its correlation to the outcome or the target. And then we can measure whether or not it had a very significant value or a very small value. And that's how we can stack rank and determine which one of those, which of those features is most important to least important based on the classification metric. If it broke the model horribly to shuffle the data around, it means it's very important. And if you shuffle the data around and it doesn't have any effect on the outcome of the prediction at all, then maybe you don't even need that feature or column. We go along the business of trying to choose which kind of algorithm we want to use. And there's a lot of different algorithms, but they generally fall into two different buckets: linear models, how do X and Y correlate for each one of those features, and tree-based models, which go through a dialectic of decisions, yeses and nos, until they filter down to the leaf nodes where we actually have concrete values. And so we want to be able to automate the process of going through a bunch of different types of models and finding the ones that work the best. Otherwise, we have to, invent or innovate our own processes. And when you do that in code, you start to actually produce an AutoML capability of your own, which I've done. Ultimately, we want to produce models that fit very well. And so there's a bit of a spectrum between underfitting and overfitting. And underfitting is a situation where your machine learning model doesn't learn enough about the distribution of the data. And so the predictions are naturally inaccurate because you haven't learned enough. Then, you can memorize or overfit the data that you have at training time, and it becomes so specialized, it'll produce an absolutely perfect result at training time when you evaluate it. But when you put it out into a production environment, it's not very accurate because it's overfit. So what we aim for is something in the middle, something called generalized, where it has learned the pattern of the data sufficiently. It's learned its variability well enough that when I put it into production, it performs very similarly in production to the way it performed when I trained it. And again, I'm discussing all of this because this is what AutoML is doing for you under the hood. It's using techniques like splitting the data into a training data set to teach the model all of the information, kind of like when we were in school and, the teacher gave us a bunch of information, and then later on they gave us a test and they had the answers in the back of their teacher's book just in case they didn't know how to do the math properly. But when we hold out some of our data, something like 20 or 30%, we essentially are producing the answer code in the back of the teacher's manual so that when we run predictions on some data, we can compare it to what the true answer is and determine whether or not the model predicted properly. Another technique, which is more computationally expensive but more accurate, is called cross-validation, where we break it up into a number of folds. And in here, I'm showing 5-fold cross-validation. It's often called K-fold, K being, the placeholder for the number of folds that you specify. And we also have a tendency to take maybe 20% of our data as soon as we get it, and we put it aside. And we're not going to use it to train or even evaluate our model. But then once we've selected the best combination of algorithms and features and things, we're going to take all of our data, all 5 folds plus our 20% holdout, and train it again to make that model even better than it was when we validated it. But in cross-validation, what we do is we cycle through using one of the folds to validate the data and the remaining other 4 folds to train the model. And so what we wind up with is, you can see here through the graphic, we might use 1 through 4 on the first run and validate on fold number 5. And then on our second training run, we'll use 1 through 3 and 5, but we'll validate with 4, etc. I think you can follow along there. And this again is something we might choose behind the scenes to specify cross-validation. What this does is produces a very stable model, because each one of these training folds not only tells us an accuracy metric like accuracy or precision or recall or root mean squared error or something, but it also gives us the deviation, the standard deviation. And if we have a very small standard deviation from these cross-validation runs, we know that it's going to perform very well because it's not bouncing around. It's not doing great on one run and poorly on another. Okay, and so the last topic I think we discussed was those configuration settings, those hyperparameter settings. And here you can see that various data sets, and a data set can be a combination of features that we were talking about, and a combination of feature engineered features, along with 1, 2, 3, 10, 100 different training algorithms, multiplied by all of the different hyperparameter combinations that would be applicable to that training algorithm. And quickly, even when just using one data set and 2 training algorithms, and each of them having 4 different, that's 1 times 2 times 4, it starts to grow very quickly. And if I had to do that all manually, it would be very tedious, very repetitive, very time consuming. And if you're minding your expenses out in Azure, it's also using compute cycles and raising your Azure bill on you. Plus, even more expensive is your data scientist, who's making a pretty penny, is spending a lot of his time working on one model. So again, back to even our first slide, professional data scientists can use AutoML to find out quickly whether or not the data is good enough to start with, to find out which family, at least, of machine learning algorithm is going to perform better than the other, and give them a good rough estimate of what hyperparameter combinations would go along with that model and that data set, and then tune that even better moving forward. So this is our resources slide, which means it's time to go back to playing in Azure Machine Learning Studio, which I'm sure you've been waiting for, because nobody wants to be put into a PowerPoint coma in the morning. That's not the right thing. I do apologize. Let's see if we can get this right. Here we go. So here's where we left off. We had put in a data set called daily bike rentals, and in the previously I did one called bike share on the same data. And then we can come down here, and if we wanted to produce our own experiments, we could say, hey, I want to create a new experiment. But what we want to do in this case actually is go up here to our AutoML. And so I've already done one out here, but let me check really quickly. No, never mind. I'll show you how to do it first. So what you can do, of course, is first choose your data set. So, I'm going to choose daily bike rental. This is how simple it is to get going with it. It's going to go out there and it's going to show you a little bit about your data set. And I'm going to say, well, I want to create a new experiment, and I'm going to call it daily bike prediction, just for the heck of it. And it already knows what my data looks like. And like we saw, we have day and month and year, etc. And we know that our target down here is the number of rentals that we want to use. And then the reason we had to, well, we could create it here if we wanted to with a click of a button. We can create it with code, as I said, but we already have a cluster out there that I've created, so I can specify that cluster. And the next thing I might want to do is make some choices here. Now you can see it already understood that because the target I chose was a continuous numeric value, that I'm going to do a regression job and not a classification job. It could get confused here between a regression and a time series if I had a date column in there, a time date value. So I might want to, override the AutoML's decision, but here it's spot on. It knows I'm doing a regression job. We talked a little bit about featurization, and opening this interface up, we can choose featurization types, the feature type, how to impute it using mean, most frequent, things of that nature. And so it does a little bit of feature engineering for us. Now, it's not going to do all the feature engineering in the world for us, but it's going to do a little featurization. And so in here, we can make some decisions if we wanted to make changes, but it did a good job for us. I might come in here and say, it happens to be that normalized root mean square error is appropriate, but there are other R2 score or the coefficient of determination might be something you're after. It's a score where bigger is better. It goes from 0 to 100 or 0 to 1, if you will. And if it gets closer to 1 or to 100, it's doing better. And if it's smaller, it's wrong. But these are called error metrics, and smaller is better. And so very often what we like to do is measure the error rather than the accuracy, if you will. I could come down here and block off some algorithms. And in this case, so that it doesn't take a very long time to run, I'm going to block off a whole ton of these and just keep a couple of them, because it's already going to produce a large number of permutations as it tries feature combinations and hyperparameter settings. So I'm blocking off all but 2 of them. I can go in here and say, hey, I just want this to be, a half an hour. And if otherwise I want it to die. And I might say, if it's not at least 0.8, which is pretty good, it's not wonderful, it's not perfect, it's not 100%. If it doesn't give me a metric score of 80%, man, cut it off. Don't even bother training that model. Because you're just wasting my time. I don't need to see the poorest algorithms. I need to see the best ones. I could choose again. In here, we talked about validation, k-fold cross validation. We could say choose by yourself. We could use training validation split, that we talked about, train on some and test on 20% remaining. Monte Carlo is a lot like k-fold. It goes through many, many iterations of samples of the data, but instead of cutting it into, say, 5 discrete folds, what it would do, it would sample those. It would, like, say, by sample, take 75% and then validate on the remaining 25%, and then take another sample, random sample of 75% and train on the other. So that's what Monte Carlo is. So I'm going to just let it make that decision by itself. And, I can add more concurrent iterations and say, well, why don't you do 6 at a time instead of 1 or 2 at a time? And that can speed up my processing. So I'm going to save this. And that's about all I need to do. Then I can just say click and finish, and it's going to start to do that run for me. And this is, of course, in Azure Machine Learning Studio. There's a code-based approach we could take as well, but it's just going to go on. It's not started right now, but it's going to take a minute, and we can click refresh a couple of times, and there you go. And now it's in the starting state, and it's going to produce a number of different models. Here we can, it's not really running yet. So what I'll do actually is I'll switch over to an existing experiment that I have out there. And you can see this one ran to completion. It completed. This is the run itself that we can open up and take a look at. And it says, there were some data guardrails, validation, split handing. It's going to tell you what it did. Guardrails, as you would imagine, are there to prevent you from making mistakes, things that would either negatively impact the model that you produce or consume too many resources and too much of your time getting you a bad answer. So here you can read into some of this. It's then going to show you all the different models that were produced. And it's going to tell you over here some information about what was done, and you can actually view the explanation for the best performing model. This is run off of a library, an explainability library that Microsoft has produced, and you can leverage it from your code as well. But it tells you all about the model performance. It tells you a lot about, does what we would normally call exploratory data analysis. It produces a lot of the visualizations for you so that you understand the distribution of each column of the data that was used. It tells you about the feature importance that we discussed about, the aggregate feature importance. It says that working day is the most important feature, followed by temperature, a temperature, and year. And then you can also look at individual feature importance and what it's doing. This is the precedence constraints that we were talking about earlier on the slide deck, where it's showing you for each individual data point, you know, the impact that it would have had on the outcome, on the predictions that's being made. So there's a lot that can be learned here. You know, this is mostly for troubleshooting when something goes wrong. If there were any child runs, it tells you that this is the 99th run. It ran 100 runs or 99 runs. How long would it have taken you to run 99 or 100 iterations of an experiment to find, you know, which run produced the best results? And it doesn't take that long here, you know, 2 minutes and 14 seconds for that run in particular. So, you know, it gave us a model, the AutoML model, and I can actually see the snapshot for it and see how to call it. And eventually, if I put it into production, I can do some monitoring on that to see how much CPU utilization and other metrics were consumed by running this model. But at the end of the day, I chose a model, and even before this ran, one thing that's smart to pay attention to in the runs with all of the different models that were produced, these are all individual models. It used the light gradient boosting model algorithm with, this is a scalar. It chose in this case to take all of the numbers in the ranges of the numeric columns and push them between 0 and 1. Here it's standardized them. And using the random forest algorithm, it chose to take the numeric values and give them a mean of 0 and a standard deviation of 1. And so, you know, it tried a lot of different combinations, and eventually it came down with a couple of them, and then it produced something called an ensemble, a couple of ensemble. And an ensemble is when it has determined that a combination of one or more or two or more of these other algorithms put together will produce a slightly better result. And it'll tell you, hey, this is the one you should use. The ensemble methods may take a little bit more time at the inference, and that is when you're rendering a prediction on new data, than some of these. So if it's more important that you get the absolute best, see the error metric is only slightly different. If it's important you get that little bit better bit of performance, then you can put this one into production, but it might, if you're doing, you know, batches of tens or hundreds of thousands of inferences at a time, each one of those might take a little bit longer, and it might push that batch process in this case out to take a significantly longer period of time. If you say had a bike rental on a computer, you know, somebody was going to make something, you know, need a prediction in real time, like a data analyst, you know, you might want to put this one into production, because when they give it the, you know, the test data and push the button, give me my prediction, it'll return much more quickly. So there's some decision points out there to make based on which one to put into production. I put one of them into production a little bit earlier just so that I wouldn't have to make you wait for things. And that's where we wind up with an endpoint. So here's my prediction rental. All I need to do to put one into production really, however, is to go, I'll go back here to, let's just say my daily, that's still running. I'll go in here and actually choose this voting ensemble model, open it up, and you'll just see here up here, there's a deploy. I just click deploy and I say, well, you know, daily rentals. And I'm just going to test it and not put it into production for real. So I'm going to put it on an Azure container instance, you know, and I could come down here and I could make some advanced decisions about encryption and things like that if I wanted to, memory reservations, but I don't need to do that for this case. And then click it deploy, and that's it. That's all I got to do. to put one into production using the user interface. And it'll sit here and churn for a while until it actually produces it for you. I can go in here to, let me see. You can see that it's deploying there, so I can go and look at the deployment details. But what I'm going to do to keep our life moving along is I'm going to go back into the one that I already deployed. And you can see that when I go to consume, I get a REST endpoint. And so what I can do is copy that REST endpoint. And I've, again, produced this upfront. I hate it when things do not want to copy and paste well. Copy. There we go. So that tells me the address of my Azure Container Service. And if I'm remembering correctly, let me see. What else did I need? I needed my key. I think I need my key out here, don't I? Your container registry. Keys. Nah, I don't think that's what I'm being a little dumb here. Sorry. I know there's a key out there that I need to have. And I'm just forgetting where it is. I'm being a little thick-headed today. It's my birthday, so I'm working on my birthday. Throw me a bone. Well, anyway, I would put a key in there and then I could run this to make some predictions. I don't want to consume too much of your time right now with that, but that's basically how easy it is to go out and use AutoML to register a data set, use AutoML to produce an experiment with a number of runs, analyze and choose the best of those runs, push a button to deploy it, get an endpoint out here, and then go ahead and go out there and run a test on it with some downloaded data. We also showed you earlier on, however, that you could go into your computer environment and just click, say, Jupyter Notebook. And I've done that, and it produced this. Give me a Jupyter Notebook environment. And so another thing I'd like to show you is how we can use code. So if you're comfortable using the UI and you just want to knock through it that way, that's one way you can do this. And another way is to go out and use a traditional environment like Python, Jupyter Notebooks. You could also do it with R. But in this case, you know, I'm, as I normally would, loading up some libraries that I'm going to use. In this case, it's helping me to understand whether the versions I'm using are the same that was used for this notebook. Here, because I spawned this environment, this Jupyter environment in this notebook from an existing Azure Machine Learning workspace, it already knows what it is. When I first make that workspace, it creates a little file and a configuration file. And so all I have to use is the workspace library and load up that configuration. And then I can, you know, create an experiment. I gave it a name just like I typed it into the UI. And it goes out and it gets my subscription ID and everything. It knows that that's my subscription, and there's my my workspace and all of that. And here's where I could use some code just to go out and create a cluster. In this case, when I click it, it's going to go, hey, I already found that cluster because I already created it. But this is how easily, just a handful of lines of code, and it's all boilerplate. You can get it right out of documentation, or once you've stood up a workspace, you can go and look at the example notebooks. And actually, this is one of them. So you can find most of the code that you need to do your work. Frankly, it's a matter of how you put it all together. It determines how well your models are going to turn out. Here, I can just go out on the internet and download that file and load it into a pandas data set, or actually use it to make it the data set. So everything that we did in the user interface when I went to my local machine, I just did that in, you know, like a second by clicking a button and running 4 lines of code. So it's gone out and it's registered a data set. And it tells me, you know, what I'm going to do when I run this task, gives me some description here in this notebook. But what I'm going to do is I'm going to load up some AutoML settings. So a lot of the configurations that we made using the UI, they're all just right here. You know, I decided to use threefold cross validation. I chose average precision score weighted as my metric. I decided to enable stop early learning. That was where I chose 80% as a threshold. It will, if it knows it's not going to produce a very good model, instead of wasting your time and energy on the compute cluster, it'll just abandon that. And I can configure all of this in a quarter of an hour. I chose 2 concurrent configurations, and it stuffs that all into an AutoML configuration. And I can go out there and kick off a remote run. And, you know, it's going to sit here, submit the run, and begin to produce a bunch of different iterations. So I'm going to come down here and load up the run details. This is a widget, you know, it just helps show us what's going on. And you can see that it hasn't started yet. It's waiting for the runs to be produced, but it's going to go ahead and it's going to run all of these runs, and it's going to start to look like this, you know, pull it out of the oven for you. It ran all of these, and unfortunately the widget has stopped displaying. But I went and I was able to go and look for the best run just through some code, retrieve the best model. And so I'll go back to the previous one. Here it's still running for us. It's going to take quite a while, quite frankly, which is why I have the other one. But, you know, we'll wait for it to complete, and we'll explain. That is, we'll look at, you know, all the details about why it was the best model. And then we can retrieve that model from the collection of models that we produced, and we can run a test against it, and then calculate the metrics. And essentially that will tell us how well our run did. So here, as I step through, you can see, you know, it produced that, and it produced what's called a confusion matrix. And this is a very popular way of determining whether a classification algorithm has performed well or not. Because as you can see, the prediction down here was a true or false. So these are true positives, where the true lines up with the true here, and it said it got 92 of its trues correct. And on the diagonal, it shows an actual false and prediction false. 56,978 were correct, and only 8 of them were not correct. So I got 8 wrong, and I got 56,978 true. That's pretty good, but it's telling us that in this notebook, which has to do with credit card fraud, that most of them are not fraudulent. And what I'm looking for, these true positives, 92 were positive, although I did miss 18 of them. 18 got away, instances of fraud. But, you know, that's, you know, what, 110 out of 56, you know, over 56,000 of them. So this gives us a pretty good idea that the model we produced did very well. This is just showing you how you can do this in code. And what's really kind of important for you to know if you're experimenting with all of this is that if I go in here to notebooks, it says samples right here. And what I can do is go into any of these tutorials or how-tos on deployment and explainability and anything like that. And all I would have to do, say I would like to clone these. And when I say clone, it's going to say, where do I want to put it? And, you know, I'll put it over here in my user directory. You can't actually use or change these. This is like a, you know, a library for you to use. But then look, it just produced this for me, and I can go in and begin to use any of those notebooks to find my way around. And in here, I've chosen to use these classification credit cards. So, you know, you can see here where, you know, I can actually open it up in here, or I can open it up with, you know, Jupyter Notebooks, which I like better. Now, but you can do the development right in here, but that's how easy it is to get a hold of these workbooks and start playing with them. But in this case, we see them over here in the Jupyter environment where, I'm more comfortable. It looks better to me here. You can do all of this in code. So anyway, that kind of brings us really close to the end of our hour. And again, what I might want to remind you of is that, oops, I don't know why that's there, but we have a number of resources, and what I'll do is I'll make sure I'll send out a copy of this deck for your use in your learning with AutoML. Obviously, Azure Machine Learning's documentation as a whole is a very important resource. All of the tutorials and how-tos are actually in documentation. So all of those notebooks I was just showing you are actually the code that goes along with all the tutorials and how-tos. In this case, what is automated machine learning? There is a subsection of the documentation that explains in greater detail what automated machine learning is, but I hope that I covered it pretty well for you. There's also a Microsoft Learn module. As you may understand, everything in today's DataFest is corresponding to some Microsoft Learn learning out there. And so using AML and auto machine learning is the course that goes along with it. It's really simple and very similar to what I just did for you. And then when you go to use your own Python or R notebooks, here's a reference that tells you how to use auto machine learning with Python from Jupyter Notebooks, which I just demonstrated for you. And so with that brings us to the end of the demonstration and the presentation as a whole. If anybody has any questions now, I'd be more than happy to answer them for you.
You guys can take yourself off mute and ask in the chat, however you want.
So thanks, John. I see a couple of questions in the chat window. So
okay.
The first question is from Shrikant. He is asking, what are the implications of this AI data solutions? If something went wrong, who would be responsible? Persons to govern the result?
That is an outstanding question. And just as a shameless plug, at Microsoft, we have something called FairLearn, which is a set of Python libraries that help us to mitigate bias in data and machine learning models, because ultimately, let's just say I have a customer, XYZ Corporation hires me to build a predictive model, and they choose to put it into production. It's their model. They're the ones making business decisions based on that model. As a vendor like Microsoft, I will have a contract with my customer saying, I'm going to give you the best thing that I can. I'm going to show you how we have explainability features that can explain why each individual decision or prediction was made so that we could justify something. So if somebody applies for a loan, or even worse, applies for to get out of jail, I forgot what that's called because, I'm not a jailbird, but nonetheless, you can say, hey, the reason we declined your application for a loan was, right here, because your credit score was kind of low, and that correlated very highly to the fact that you were more than 90 days late on several payments within the last 3 years, and so they can't complain. But, that responsibility ultimately lies with the business that chooses to use the predictive service to support making their decisions. We as technologists need to be responsible, i.e. some of those libraries we can use to explain how decisions were made and during the development process. So as a data scientist, I can see what criteria are being used. I would never want to choose to use something like gender or race or religion. Oh my goodness, that would be a storm of liability. But what's important to realize is even though I may exclude features like that, subtle bias can creep into other things, like, that otherwise inane features that you would never believe have those bias. Our FairLearn library helps us to remove those and mitigate those biases in the remaining data set features. But ultimately, as the vendor, the data scientist, it's our responsibility to satisfy a contract to produce the best possible result. And that may include saying, given the data you've given me, you can't have an accurate prediction. It's not very good. There's no way I would put this into production, versus producing a very good result and saying, I think you'd be very safe putting this into production. But ultimately, it's the customer that is responsible for the decisions they make. We just need to give them the tools to justify and explain those decisions to their clients or customers.
Hey, John, we're bumping up right against Veronica's time. So thank you very much for presenting and taking the time to give to the community. And, you know, I look forward to, you do a great job when you speak at our events. So I'll look forward to having you back in the near future.
Thanks so much, Tim, and have a great afternoon.
Thank you very much. I'm going to stop recording.
Okay.